we'll continue. Next lesson. Materials, and now we're on 6 here. Suppose you weren't watching the videos while you were out.
I studied master.
No, you didn't.
No, I saw
I can tell you. Yes,
something that says GIST property, ordinary level, something 3 or something.
Maybe I believe you.
Yeah,
I also follow the second teacher.
I was with me yesterday.
He's not a great witness because he's having attendance issues as well, particularly at 9 o'clock. So I wouldn't have him vouch for you. All right. Next one. So specific heat capacity. Okay. Yeah. Right. You got the title? Guys, you got this? Yes, specific heat capacity. Mir, come on. Write the title down. Mir, yes, we just did a tutorial today, okay? You got the title?
Yeah.
Okay. Specific heat capacity. Right. Why does metal feel colder than plastic? So, for example, if you have water at 10 Celsius and air at 1 Celsius, in fact the water will feel colder than the air. So it's not enough just to talk about temperature, there must be something else. Also, you'll notice that metals will feel hotter sooner than plastics when you heat them. So metals will get hot quickly, whereas plastics don't. In fact, conductors will feel hotter than plastics when given the exact same heat energy. So if you put some heat into plastic, and you put some heat into metal, and you put the same amount of heat, so let's say you have 1 kilogram of plastic, 1 kilogram of plastic, 1 kilogram of metal, you give them the same amount of heat energy, but the metal will feel hotter than the plastic. Some materials warm up faster than others. Why is this? Well, it's because different materials have different ability to absorb the heat energy. And it comes down to something you would have learned in chemistry. Some materials are conductors and some are insulators. So conductors will take the heat energy easier than insulators. All stuff you know from chemistry. So it gives us this concept called specific heat capacity, which is just the amount of energy you need to raise 1 unit mass by 1 unit of temperature. So in other words, it's how much energy you would need to raise a kilogram of it by a Kelvin, or Celsius. Or sometimes it's given in grams, so you could say it's the energy required to raise 1 gram by 1 Celsius. So this definition is actually something pretty common on the exam, and most people get the definition wrong. What do they forget to say? Most people say the specific heat capacity of a material is the amount of energy required to raise. I'm thinking most people get this definition right. It's the next one, the latent heat, which people get wrong. What's wrong? This one should be okay in the exam. Is latent heat a separate lesson, or is it going to be in the same one? No, it is a separate lesson, okay. Mm-hmm. Do you talk about this in chemistry? No?
This topic is also the part of chemistry.
Yeah, have you talked about it in chemistry? No? Okay, continue.
By ionic option of
Temperature.
Yeah. So, I want you to think about what the what the units are. So, what's the units here for this?
kilogram farad.
Kilogram per joule.
Kilogram Kelvin. Per.
No. Stop guessing and think.
Required to raise by
You have 1 kilogram, and you put some energy in it, C, or rather, you put some energy into it, and it increases by 1 Celsius. So it's how many joules you need to raise it by 1 Kelvin or Celsius, and you have 1 kilogram. So it's like joules per kilogram and per Kelvin. So in other words, it's joules per kilogram per Kelvin. It's how much energy you need to raise it for each kilogram for each Kelvin. So this is the unit of it. Or sometimes it's given like this, grams and Celsius.
Like is it
No, we use this one. Huh?
if there's a numeric like this, there's a problem. So we need to convert the units, or it's fine.
You should convert them. Okay. So, using this definition, we can come up with a formula. When you have energy delta Q, and you want to increase m kilograms by a temperature delta theta, this is increase, you can get it from this formula. So the amount of energy you need to increase the temperature by delta theta is just equal to the mass times the heat capacity times the temperature change you want. C is heat capacity, and delta Q is the energy required, m is the mass, and delta theta is the change in the temperature.
C is constant.
Yeah.
For each material.
Yeah. Is this the definition?
It's more just the formula. Yeah. Continue? Okay, so let's have a look at some values of what C could be. So, let's start off with water. So, just so you're clear, what you're saying here is that if you have 1 kilogram of water and you want to increase its temperature by 1 Kelvin, you will need 4,181 joules. Do you understand what you're saying here?
Would it make a difference? It was like from 99 to 100, or from 1 to 2?
No, it doesn't. It's just, for those two examples, it doesn't, no. So it's the same if it's 1 to 2 or 10 to 11. Okay. Next material, you should write these down because you'll need them for the questions. The next material is ice. So interestingly, for ice, if you want to warm ice, you don't need as much energy. For if you want to go from say -5 to -4 Celsius, then you need 2,000 joules for every kilogram. No, just write it down. I don't like this. Write it down. I'm not going very fast through these.
It will be given in the exam.
I know, but just write them down, please. For me.
Yes, for you.
Thank you. Okay, so that was ice. The next one is steam. And again, steam doesn't need as much energy to raise its temperature. About 2,000 joules per kilogram per Kelvin. Yeah. Okay. Next one is copper, and notice the big difference now. With copper, you only need 385 joules to raise a kilogram of copper by a Kelvin of temperature. So that's a big difference, like 10 times different. The next one is milk, just because I think I have a question to do with coffee. Milk is it's not as much as water. It's 2,850. So water is still the highest so far. Alcohol, again, not as much as water, 2,300. Lead, Pb, it's tiny, only 129. Very, very low. Very, very low. What's what?
Yes.
Pb. You know this element? You know this. You must have done this with Lorraine. Pb, lad?
Yes, very.
Have you?
Yes,
I hope so. Air. So for every kilogram of air, if you want to raise the temperature by a Kelvin, you need 1,000 joules. Yes. Okie dokie. Water is very unusual. In fact, one of the reasons water is important for life is because it has such a high heat capacity. Since we are mostly made of water, it means you require a lot of energy to change the temperature. So it's kind of like water acts as a good storage of energy, of heat energy, because it requires so much energy to heat up, So that fact that water is so big is important. Nothing else really comes close to water. When you look at even ice or steam, it's only half what water is. And then when you compare it to milk, alcohol, and other materials, it's just much, much bigger. Liquid water is twice as big as anything else, practically. Okay. Why do different materials have different heat capacities anyways? It's complicated. And we might look at it later, but it's quite complicated, so we don't have to worry about it right now. We just have to accept that different materials will have different heat capacities. Right, so here's a little question we can do together. You don't have to write it down. How long would it take to boil enough water to make a cup of tea by using a small 1 kilowatt electric kettle? So, we'll do this one together as an example. We have an electric kettle. Oh dear. And we have some water in it. And we know that the power here is 1,000 joules per second. Right. How much water should we put in it to make our coffee or tea? So let's estimate the mass. Come on. How much water would you need to make a cup of coffee or tea?
350 milliliters.
liters. Yeah. Let's say you put in. Let's just say you put in 0.5 kilograms.
Yeah,
0.5 of a gram would not be much water. Right. Now, what temperature would the water be at the beginning? We'll call it θ1 when you take it from the tap. What temperature would the water be from the tap? 29.
10.
10. 29. I don't know. Do you live in a homestay? Or you live with your sister? Does she have hot water all the time in the house? 29 Celsius. That sounds like paradise to me. My water comes out at 10 Celsius. Okay. But I thought I heard you say 0.
Yeah.
Yeah.
I swear it's right, I'm saying it right, because from my tap it's so
0.
it takes time to from the
Yeah, but if the water was at 0, wouldn't it be ice?
it's like approximately to
Yeah, okay. Now what temperature do we need the water to reach?
100,
100.
Yeah.
So what's the change in the temperature?
90.
90. Okay. So how much energy do we need? Well, the energy we need is mc delta theta, which is 0.54181 90. Yeah, tell me what that is, please.
It's too much.
No. 363.
Not 363.
But it should be in Kelvin, yeah? Or
It doesn't matter because it's still 90 Kelvin difference, because it's only the difference you cared about.
Oh, that's what I was doing. I was converting to Kelvin.
No, but if you convert this to Kelvin, watch, this would be 283. This would be 373, so the distance is still 90. Yeah, so it doesn't matter. So what is this then, please? 90 times 4181 times 0.5.
Yeah, it's a good thing.
188, 145.
188, 145 joules.
Yeah.
Now, power equals work over time, so time is work over power. We need to do 188,145 joules of work, and we can do it 1,000 per second. So 188.1 seconds, or about 3 minutes and 8 seconds. So about 3 minutes is the amount of time it would take to boil the water. A realistic number. Yeah. Okay, so this is our first example. Not mad difficult, but it shows you the type of questions you get with these. Okay, if you can write this one down. Yeah. Okay, continue. No. Come on, Mayor, get off the phone. What are you doing? I'm thinking about at the end of this chapter giving you a test on it, because we don't really have a mid-semester 2, so I'd like to see how you're progressing or not progressing.
We don't have any mid-semester to, like,
So maybe I'll give you a test to see how you're progressing or not progressing.
but we will have a mid-semester to exam.
I don't know if you will or not. I'll give you one anyways. I need to keep my eye on you.
Yeah.
Alright, back to the slides.
Oh, nice.
Yeah, maybe I should do something for maths too. Right. Here's one I want you to try and then I'll do it. You have 100 grams of ice at -10. You leave it in the sun and it will increase to -1. And my question is, how much energy did the sun give the ice to do this?
Just delta Q.
Just the delta Q. Yeah.
Theta 1 must be -10.
No. Oh, theta 1. Yeah, theta 1.
How will we know that the temperature is theta 1 or theta 2?
No, you don't even have to write theta 1 or theta 2. I just wrote that to make it clearer. You just want to know what the difference in the temperature is. So you can just automatically write delta theta. So how much has the temperature increased by?
9.
So just write delta theta equals 9.
But it's -10 and -1.
Yes. To go from -10 to -1, you add 9. Right? Or not right? Don't break my heart. Uh-oh. What's wrong? You don't seem happy.
The change in temperature is T2 minus T1.
Mm-hmm.
So T2 is -1 and then
Don't
we have plus.
think of it this way.
Yeah, you're making it awkward. Okay, -1 minus -10.
-1 plus 10.
Yes. Which is
Yeah.
9. Yeah.
Why do you have to be mathematical?
No, it's being awkward about it.
KT minus 1. K minus 1.
Mm-hmm. You got an answer? Right, I don't even have to write this down. Where's your calculator?
I'll buy today.
Right, what's the formula? M times C, and what's the C for ice?
2110.
2110, and the delta theta?
9.
That's it. So that's, what's that? 1.9 kilojoules of energy was given to the ice by the sun. I really hope you got that.
Yes.
Good. Okay. Here is another one to try. I feel like you could do it. Yes. It just looks more difficult than it is. So you have an electric heater, and it's a 3 kilowatt heater, and you're using it to heat a room that's 10 by 10 by 5, and the room is at 10 Celsius, but you would like it to be at 20 Celsius. And you can take the density of air to be about 1 kilogram per meter cubed. How long would it take for the room to reach the temperature? So it's a little bit like my question with the electric kettle and the previous question. It's like the two together. And my hint is first work out how much energy is required, then get the time. Yeah?
You want the
Q first.
yeah.
Yeah.
No.
Yes.
The theta.
No, first thing you should calculate, okay, delta t defined is 10. Then delta q.
Wait. What? I have it.
How will I found the mass?
1
kg.
What?
It's out in the question, take it as 1.
Oh, that's it.
What do you mean? Oh, the mass
No, the density.
is 1 kilogram per meter cubed.
That is like the unit, isn't it?
Oh yeah, the unit is kilogram per meter cubed, so it's 1 kilogram per meter cubed.
So the mass is also 1 kilogram?
No, because you have more than 1 meter cubed of air.
So we multiply it by the area?
Oh guys, you're breaking my heart here.
It's
Breaking
like
my
one.
heart here. You know the formula for density. What is it?
M over
M over
V.
V.
But the volume of room.
Oh,
It's
it's
10 by
10
10 by 5.
Yeah, the area. Oh, the volume.
You're killing me here. Killing me here. Literally killing me here.
No, but this is.
I can feel my life
this is
being
what I
sapped
mean.
out of
We
me.
get the first and multiply it by 10, 10, 5.
Yes.
Yes, so it's correct.
Yes, so don't ask me this. You know it's correct.
I don't. That's why
No. That's what I mean. You should know it's correct. Don't ask me this, please. I can feel my life draining out of me. Okay, come on.
Which capacity do we use?
It's air.
1, 0, 1, 2. 1, 0.
Yeah.
Mm.
If the statue is so big.
Yeah.
Yes. I'm doing it for both.
Ask me here.
5060.
1, 2, 3, 4, 5, 6, yes it is.
How long? Can you find the time?
Answer in minutes or seconds?
Minutes.
I think I got it.
What?
Let's have a look. So, delta Q is mc delta theta. But if you have density as mass over volume, then mass is density by volume, because you know the density and the volume but not the mass. So this you can write as density, volume, capacity, delta theta. The density, you know, it's 1. The volume is, what would I say, 10 by
10 by 5.
10 by 10 by 5, and the delta theta is 10. This is how much energy you need. Remember, power is work over time, so time,
By 10, 12.
the capacity, what was it?
1, 0.
1 0,
1, 2.
1 2. Time is work over power. So if I just divide this by power, 3000, then I have my time. This will be in seconds. So it's, what?
Did all the time.
Yeah. 10 times 10 times 5 times 10 times 10, 12
5.
divided by 3000. This is seconds. So you should have 28.1 minutes, about half an hour. So about half an hour. So you need to keep the electric heater on in this room for half an hour to heat it up from 10 to 20. Although this is assuming that it's 100% efficient, which is not, because as the room heats up, heat will be leaving the room. Also, there are other things in the room other than air that might require more energy to heat up, like tables and people and chairs. So I think in real life, it's probably going to take twice as long, because I think in real life, the efficiency would only maybe be about 50%. I'd say half the heat is lost out the window, out the door. You know, if someone opens the door, someone leaves the window open. It's going to take twice as long. Yeah. Okay. Right. One more. So a physics student is making a latte. He mixes 200 grams of hot milk at 27 Celsius to 50 grams of hot coffee at 80 Celsius. By approximating coffee as water, they're obviously not the same, but by saying it's roughly the same thing, estimate the final temperature of the delicious, warm, steamy latte. Okay. So we want to know what the final temperature will be if you mix the milk with the coffee. Now you might remember this week or last week I was saying that if this is at temperature 20 and this is at 20 and you mix together, it's still at 20. But if this was at 20 and this is at 30, the final temperature, it's not clear what it is. It won't be 20 or 30. It'll be somewhere, not 25, it'll be somewhere in between, but we don't know where. So this is our first example where we can know the answer. Alright, so I'll just draw what's happening here. In the picture at the beginning, you have 0.200 kilograms of milk. And then you have, what is it now? 0.50 grams, 0.050 kilograms of coffee, which we said is like water. So we'll just say it's water. Okay. I couldn't find the heat capacity of coffee online. I think this is why I said it. I could find it for milk, but I couldn't find it for coffee. Okay, the milk is at temperature of 27 Celsius, whereas the coffee is much hotter, of course, because it just came out of the espresso machine. So that's 80 Celsius then. And then you're going to mix them together, and you're going to be left with some mixture of milk and water at some temperature we call X, and this is the temperature I'd like to know. Do you understand? Yeah. Okay, so let's see what we're saying here. I know we mix them together, milk and water, but in our picture it's good to draw them still separate, because it makes it clearer what to do in the calculation. So what happens here? The milk was at 27. Will it be warmer or colder after you mix it with the coffee, the hot coffee?
Warm.
It'll be warmer. So the milk rises in temperature. And the coffee, will it be warmer or colder when you mix it with the cooler milk? It will be colder. So we can say that this one will, the milk will gain energy, whereas this one here will lose energy. But remember, conservation of energy says the total energy remains unchanged. So whatever this one gained, it must came from this one losing it. So in other words, the energy gained by the milk must equal the energy which was given up by the coffee. So here we have N. The energy gained by the milk must equal the energy that was given up by the coffee. Yes? Right. So M, what's the M, the mass here? 0.2. C, what was the C for milk, please, on your table?
2850.
2850. And let's say the temperature at the end is X. So what is the change in temperature of the milk? No?
27 plus X.
No.
Minus.
Yes. It has become X, whereas previously it was 27. It has increased to X. So the difference is X minus 27.
Why is it not finished? Because that is the message.
This is 27. It increases to 30. What's the increase? Is it 57?
No.
It's 3. So it's a minus.
So it must be 27 plus X.
No, but X is the temperature.
X gain.
X is the temperature at the end.
Temperature.
Not the increase. X is the final temperature. Final temperature.
Yeah, you want the
Change. Yeah. I know this. You know this? You know it now?
Yeah.
Great. Okay. Now, what's the mass of the coffee? 0.05. What is the heat? 4181. And now, think carefully what is the change in the temperature. And remember, it's going from 80 and it's decreasing to X.
80 minus X.
80 minus X. Now, does that make sense? Imagine a number here. Imagine this number was 50 and it previously was 80. So it decreased by 30. 80 minus 50. 80 minus X, for example. Right, can you solve this?
Yes.
Certainly can. What I'll do to make this a little bit easier is I'll divide by these two. 0.05 and 4181. So let me just grab the calculator here. Fraction 0.2 times 2850 over 0.05 times 4181. So that's 2.727. 2.727 X minus 27 equals 80 minus X. So 2.727 minus... No, did I divide that by 60?
That was the one.
Oh, that's it there. Times 27 minus 73.62 equals 80 minus X. I've lost my X there. So if I take that X to the left, I'd get 3.727X because I add on 1. Sorry, it's a bit messy, I know now. There's an X there. Take that to the right and it will be 80 plus 73.62. So then finally I have this. So my final answer, 80 plus 73.62 over 3.727 and 41, which seems like a sensible answer. It should be somewhere between 27 and 80, and it's 41. This is a typical exam question. They like doing these mixture questions in the exam. They're not really much more difficult. You just have to be careful, that's all. Sorry, that's a bit messy here. This should be it next. Okay. Mayor, you have this? Who are you texting? So what are you doing? Huh? Checking mail. Have you studied this before? It's new?
We studied this in 10th grade in Europe.
Studies is not, this type of questions, no.
Okay. You have it, yeah?